Imagine for a second a bone shatters. Not a clean break, but a complete mess. And the standard metal plate they have just won't work. For years, the only other option, a custom-made implant, was way too slow and incredibly expensive. But what if all of that was about to change? Today, we're diving into a groundbreaking technique that can create a perfect fit implant pretty much on demand. And believe me, it's changing everything we thought we knew about healing. So, here's our roadmap. We'll start by unpacking the real-world challenge that surgeons face. Then, we'll get into the brilliant new way of forming metal that's solving it. We'll follow the entire journey, right from a patient's 3D scan to a finished implant. And then, we'll look at the hard data to see if it actually works. And finally, we'll explore what this all really means for the future of medicine. All right, first things first. Let's really get to grips with the core problem here. When a surgeon is looking at a truly catastrophic injury, why is that one-size-fits-all approach just not going to cut it? Okay, so picture this. A major fracture at the very top of your shin bone, right where it meets the knee. We're not talking a simple crack. We're talking the bone exploding into a bunch of tiny pieces. You can't just slap a standard flat metal plate on that. It just can't hug all the unique curves of the bone to hold everything together securely. It's like trying to patch a shattered vase with a piece of cardboard. And that really gets to the heart of the matter, doesn't it? A custom-fit implant is obviously the best solution. It's designed to match a patient's unique body perfectly. But the old way of making one? It meant building these massive, expensive, custom molds. And that process is just painfully slow and way too costly for a part you're only going to use once. It's been a huge roadblock in giving patients the best possible care. So, how in the world do you solve a problem like that? Well, you don't just tweak the old system, you throw it out and start fresh. Let's get into the innovation that tackles this challenge head-on by completely reinventing how we shape metal. It's a bit of a mouthful, but it's called Incremental Sheet Metal Forming, or ISMF for short. The idea is actually beautiful in its simplicity. Instead of using a giant mold to stamp the metal into shape, you have a robotic tool that essentially draws the final part onto a flat sheet of titanium. It just gradually pushes and prods the metal into a complex 3D shape. And here's the magic word, it's die-less. No molds, none. And this table just lays it all out perfectly. On the left, you've got the old way. Super expensive, slow, and rigid, all because of those custom dies. And on the right, ISMF. It's fast, it's flexible, and it's cheap for one-off parts, precisely because it's die-less. This is what unlocks the power to create unique, complex parts whenever you need them. Okay, so the concept is brilliant. But what does this look like in the real world? How do you actually get from a patient's shattered bone to a perfect fit titanium implant sitting in a surgeon's hand? The whole workflow is this seamless dance between the digital and the physical world. It all starts with a super accurate 3D scan of the patient's actual bone. From there, engineers use that digital model to design an implant that fits it like a glove. Step 3 is all about turning that design into a set of instructions, basically a toolpath for the robot to follow. And then, finally, the machine takes over and sculpts the final implant from a sheet of medical-grade titanium. Look, a new process sounds great on paper, but the billion-dollar question is always the same. Does it actually work in practice? Now we get to the good part, the proof. Let's dig into the data and see how the final product held up when they put it to the test. You know, to really perfect the process, the researchers had to figure out the best tool for the job. They tested 2 different kinds of tool tips. You can think of it like this. One tool was a solid tip that kind of drags across the metal. The other was a freely spinning roller ball. The whole point was to see which one could create the highest quality part. And the results? Well, they were seriously impressive. First off, accuracy. The final implant was a near-perfect copy of the digital design, off by only 0.5 millimeter at most. That's tiny. Second, force. It really didn't take a whole lot of energy to shape the metal. And third, strength. The titanium sheet got a little thinner, as expected, but in a very safe and predictable way. This proved the whole process was both incredibly precise and efficient. But here's the thing. For a piece of metal that's going to live inside a person's body, the shape is only half the battle. The surface has to be immaculate. Any little bit of roughness can cause irritation and major problems down the line. So the smoothness of that implant is absolutely positively critical. And this is where things got really, really interesting. I mean, just look at this chart. The rigid tool, the one that drags, it created a pretty rough surface. But the rollerball tool, whoa, it produced a finish that was just dramatically smoother. The difference isn't subtle. It's a night and day comparison. The rollerball was the clear winner. Let's put a hard number on that. Just by switching from a dragging point to a smooth, rolling ball, the researchers created an implant that was over 4 times smoother. Now, that's not just some tiny improvement, that's a massive leap in quality. It means you get a final part that is so much safer and way more compatible with the human body. So, let's step back for a second. We have a way to make a higher quality implant, and it's also faster and cheaper. So let's zoom out and really think about what this breakthrough means for actual patients and doctors in the real world. This technology is a total game changer. It makes custom implants affordable and accessible, which could take them from being a rare luxury to the new standard of care. It slashes those agonizing waiting times from months to maybe just days. And it's not just for knees, right? Think custom plates for the skull or for complex fractures in the jaw or collarbone. And maybe the most important part, it lets surgeons hold the perfect custom tool in their hands before they even walk into the operating room. That means better planning, which means better outcomes for patients, period. In the end, the researchers' own words really say it all. They proved, successfully, that you can create these incredibly complex parts without the old, slow, expensive dies. It's not just a theory anymore. It's a practical, effective way to create real-world medical implants that can change lives. You know, this kind of breakthrough just blows the doors wide open. It leaves us with this incredible question. If we can now affordably create custom-fit parts for our bones, what's next? Custom heart valves? Personalized joint replacements? The ability to tailor medicine perfectly to each individual person? It isn't science fiction anymore. It's happening right now. The future of healing is literally being built, one perfect fit at a time.